Hello, y'all. Welcome to lesson 54 of my DP chemistry curriculum. We're going over structure 2.2.16, which is hybridization as the concept of mixing atomic orbitals to form new hybrid orbitals for bonding. So we'll analyze hybridization and bond formation in molecules and ions. We'll identify the relationship between Lewis formulas, electron domain, molecular geometry, and hybridization. And then we'll predict geometry around an atom for its hybridization and vice versa. We'll include both organic and inorganic examples, and we're only covering sp, sp2, and sp3 type hybridization. So without further ado, let's begin, and let's begin with one of the best elements for this. We're going to look at carbon. So carbon, generally when we look at hybridization, it's also helpful to have an energy level diagram. Carbon has an energy level diagram like this. We have our 1s orbital, our 2s orbital, and our 2p orbitals. Every future diagram, I'm not really going to draw the 1s anymore just because it doesn't matter that much for this. And for the 2p, actually, I'll break this up into our three discrete orbitals for our px, py, and pz orbitals. So this is carbon, and this is the energy of each orbital. You'll notice that within carbon, we only have two singly occupied orbitals. Now, these have importance because these are where bonding occurs. So from looking at the energy levels of carbon, we would pretty much assume that there's only bonding in 2p orbitals. Therefore, we expect two bonds. But that's the thing. We know carbon makes four. Like anyone who's drawn enough Lewis diagrams, we know carbon makes four bonds. Now it could be two double bonds, a triple bond, a single bond, or uh, four single bonds. So like we have examples. We know that in methane, CH4, we could do CO2. We could look at diamond structure. We could look at hydrogen cyanide. No matter what, carbon's going to have four bonds. It's going to share four electrons of its own shared. So what happens? How do we go from these two singly occupied orbitals to four singly occupied orbitals? In fact, we only have one open orbital anyways. So what happens? Because it's four valence electrons are all going to bond. So this happens through a process called excitation. So in excitation, especially during bonding, what happens is the one, or sorry, not 1s, uh, 2s electrons can be excited from ground state. And this happens when energy is added or absorbed. We're not going to concern ourselves very much about the added energy right now, but we will look at it when we start talking about things like enthalpy and reaction energies. But for now, we'll just understand that we can excite these electrons. So now we have a new energy level diagram, and this is now in the excited state. I'll just start referring it to excited, and once again, I'm not going to be drawing the 1s anymore, 2p. So what we get now is an energy level diagram that looks like this. And now we have one, two, three, four, and I'll change that. We have four singly occupied orbitals. Now the problem is this still doesn't answer everything because even though we have four singly occupied orbitals here, the issue is one thing we know about methane, all single bonds in methane, which once again is CH4, are the same. The problem is these will not form equal bonds. These will all be equal, but they will not equal the bond from the s orbital. Specifically, the shape, the size, the strength, it's all going to be different. So what ends up happening is that we actually have our orbitals hybridized. So we create a hybridized state. Now, with the hybridized state, what I'm going to do is I'm going to draw our standard 2s and 2p orbitals. But what we actually get is somewhere in between. This is our sp3 hybridized. Because what ends up happening is that these hybrid orbitals are kind of like an intermediate between our s and our p orbitals. So that's the key thing here. Our sp3 hybridization, and we'll talk about what that means too, is specifically a process in which orbitals mix to produce hybrid orbitals of equal and intermediate, that's not how you spell that, intermediate energy. This is very similar when we talked about hybrid resonance structures having intermediate properties like bond length and bond strength. These orbitals have intermediate properties of the s and p. Now we call it sp3 because we use one s orbital and three p orbitals. Not the 1s, but specifically one singular s orbital and three triplicate p orbitals. So this is why we call it sp3. So the things to note here are that it is of an intermediate energy, they're all of equal energy, and they're all identical. So what does this actually look like? Well, it turns out because they have intermediate properties, something else is that hybrid orbitals have intermediate shapes. So they have different shapes from our normal ones. Oops, different shapes. And you are required to know this for the DP exam. So what I'm going to do here is draw our simple X, Y, Z axis. And I'm going to duplicate it a few times. So sorry for my cheating here. Nope. X, Y, Z. I'm going to need to fit 4 in here. No, you know what? We'll delete this one. We'll shrink all of these. There we go. All right. So normally we have our s orbital, px, py, pz. So make sure you know how to draw these. S is just a sphere. It goes across all of them. You don't need to add three-dimensionality for the DP exam. Just a circle will always work. Our px orbital is an even dumbbell, even though I can't draw very evenly. Py, once again, this dumbbell shape, and pz, this dumbbell shape. So these are our standard orbitals. However, when they hybridize, they become new. So this is what's going to become sp3 hybrid. And we can show them all on the same plane as well. So what I'll do here is once again copy our axis. I'm going to go ahead and delete our p orbital. And we're going to put all 4 of them here on the same axis. Now, the thing is, they do have this new shape. This is our sp3 hybrid orbital. And how do we actually see what it looks like? Well, we have one that goes vertical across our z-axis. And again, these are, you can kind of rotate them if you wish. We have one that comes out And I'm going to try and use a different color for each so that you can really see the differences. One that comes out, and then once again, we're going to have one coming out almost through the page. You'll notice that this makes our tetrahedral of 109.5 degrees, which explains also our general angles of our tetrahedral shape of things like methane. So our sp3 hybridization occurs when carbon makes 4 bonds. And remember, the size is where there's greater electron density. So we're going to have more electron density here, 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 and here, with very little on these little nubbins that come out the other end. So this is basically what's happening when you have your orbitals hybridized. They're all equal, and they form this tetrahedral angle that you can identify them from. We'll actually get into that in greater detail as well. So with that said, we also have other types of hybridization. One thing that we can see that in is when we go to sp2 hybridization. So sp2 hybridization comes from when we have not just single bonds. So this is for double bonds. Sometimes we can do it in other ways. Sometimes it doesn't have to be double bonds, but we'll see those examples when we get there. So usually we have it in double bonds when pi bonds are required. So if you remember from our last lesson about sigma and pi bonds are specifically the overlap of p orbitals laterally. So it must be p orbitals, not sp orbitals, but specifically a p orbital. So we see this when we look at an example, which would be ethene, which is C2H4. So before we get into this exact example, let's look at the energy of the orbitals in ethene. And once again, we're going to do some energy level diagrams. So, and like I said before, I'm just going to skip the 2s orbitals. Or the 1s orbitals. I'm just going to go to 1s and 1p. Or sorry, I'm skipping the 1s and I'm just going to the 2s. So here we have our 2p, 2s, and this is our ground state. Now, I'm going to shrink this a little bit so I can fit 3 of them next to each other. So in our ground state, we have 1, 2, 3, and 4. Now, for bonding, we do need to excite those. I'm just going to preemptively make 3 of these. And also erase all my electrons. So when we get excited, we go up into the S and P, excited. But then here we get our hybrid orbitals. And what ends up happening is our 2p is going to remain exactly at the level it is because we're going to have one pi bonded orbital. However, our s orbital is going to go away and we're going to create our hybrid orbitals. Whoops. So we'll go ahead and move these guys around somewhere intermediate. And this is now going to form our sp2 orbitals, which you'll notice comes from 1s and 2p's. Specifically, numerically, not the 1s orbital and the 2p orbital. So we'll have these 3 at equal energy above the original s energy and the p orbital even higher. So what does this end up looking like? Well, now we can start understanding the images we were drawing in the last one, where I mentioned that we will draw orbital diagrams a little differently to represent those sigma and pi bonds. So now you can see the shape actually comes from the hybrid sp orbital. Furthermore, it's going to make that with our hydrogens. And so when we draw our hydrogens in this picture, we'll see that the hydrogens orbitals, oops, have that overlap. That's our sigma bond. So these are all our sigma bonds right here. And these are all going to be sp2 orbitals. However, this does have a double bond, and this double bond is going to be formed by these p orbitals that are going to have this lateral overlap. And so this connection, this pi bond, is coming from our p orbitals. And this is just your standard p orbital that's dumbbell shaped, even if I didn't draw the dumbbell very well. So this is what our bond of ethene looks like. A couple things of note is that all sigma bonds are going to be on the same plane, are on the same plane. And the reason we know this is because when we look at our diagram of each carbon individually, we can see that our p orbitals are vertically above and below. I'll draw that a little bit better. While our sp hybridized orbitals kind of make this triangle, and that's 120 degrees to the 90 degrees of the p orbital. So we kind of make a shape that's very similar to our trigonal bipyramidal shape that we get when we are making expanded octets. So we get almost that exact same shape here. Actually, we do get that same shape with the sp. Now, the only reason it's not is because p orbital still is only one electron domain, so this still only has up to those 4 sets of electrons, but grouped into 3 domains. So we have all these on the same plane. We can see that here where these are all on the same kind of horizontal plane with the p going up and down our z-axis. So this bonding right here is sp2 plus p. All right, so that is sp2 hybridization. The last form of hybridization we have is sp hybridization, which by the name we now know is going to be a singular s orbital and a singular p orbital, and this happens in triple bonds. Because triple bonds require 2 pi bonds, which means 2 p orbitals necessary. So when we look at our energy level diagrams, once again, we're just going to go ahead and look at our 2s and 2p. And I think I'm just faster not even doing the duplication thing. Oh, so we're still going to have our 2p, but we're now going to have our slightly higher hybrid orbitals. So I'm just going to raise this up. So this is going to be our 2s, 2p, 2s, 2p, and 2p, and sp. And so this is ground, excited, and this is going to be hybrid. Now, the example we're going to be using is continuing the same trend. We're going to be looking at ethine, which is C2H2. So we're looking at each carbon. So we should be pretty decent at these energy level diagrams now. And so we'll notice our sp hybrid orbitals are above in energy than our s orbitals, and our 2p remain exactly where they are. In our example of ethine, what we're going to notice is specifically, we're going to have two sp hybrid orbitals, and those will form our sigma bonds, and two p orbitals, and those are going to form our pi bonds. So this hybridization very much goes hand in hand with our idea of bond types. So let's go ahead and now visually reference this or represent this. So we're going to have hydrogens on either end, and we're going to have our hybrid orbitals. And hydrogens are going to have that overlap between the sp hybrid orbital and the s orbital of the hydrogen. These are all going to be our sp, 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 and sp. These are all going to be sigma bonds. And then we have our various p orbitals. So we have up on the vertical axis, so that's going to be one pi bond. And then we're also going to have the horizontal axis. So think about this on the x, y, z plane. I'm going to redo that one. So we'll get this sort of connection. That's going to be one pi bond. And then that's going to be another pi bond. And so this is what happens with the hybridization and the overlap in our various orbitals as we form these new hybrid orbitals in triple bonds. So what if we don't fully know how to draw these, or maybe we aren't confident with the electron diagrams, or we're just given an element or a molecule and we are asked to figure out the hybridization? So there's an easy way to do that. The easiest way to figure out hybridization is found through electron domain geometry. So it's not necessarily found through that, but that's the easiest way to identify it when looking at molecules and ions. So if we think about this in terms of regions of electron density, basically what I'm referring to is the electron domains, we can identify the arrangement of the electron domains, and that will tell us our hybridization. So we're making a little chart. So when we have two regions of electron domains, this is usually linear because they want to repel as far as possible. This tells us that we're dealing with sp hybridization, and our orbitals are going to line up on a plane. So they're going to look like that. And this is going to have a bond angle of 180 degrees. Now, if we have three regions of density, that always forms a triangle or trigonal planar. And that's going to be sp2. And we know that we're going to form, I want to form three bonds. So we've got our main central atom in the middle, and we have our three sp2 orbitals at 120 degrees. You'll notice when we start drawing these, we actually lose the little tiny nubbins. We don't really draw those because the region of electron or the likeliness of the electrons in those domains is very low, especially as we start adding other orbitals. Like over here in our sp, the fact that an electron will just not really be in this region because it's being repelled from this sp orbital. So our electrons really will stay mostly in the large regions. All right. Lastly, if we have four regions of electron density, we generally tend to know what this already is. That's going to be tetrahedral. Therefore, that's going to be sp3. And oof, drawing tetrahedrals is always my weakness. So if it's yours too, don't worry. And we know that's going to be 109.5 degrees. All right, so let's kind of test what we've learned. Let's do some practice. So problem 1, identify E domain, Vesper, and hybridization of boron trifluoride. So what you're going to need to do is draw this. So take a moment, pause the video, draw it, and then try and answer these questions. So when I go to draw boron trifluoride, granted, I have this one memorized because we've done it so many times, but we can do the valence electron thing. So we do step 1 of drawing. Boron has 3 valence electrons plus fluorine. Oop, I said boron trifluoride. Plus 7 times 3. So that's going to be 24 electrons that I have to draw. Boron farthest left is going to be my central atom. So step 2, we're going to draw it with boron at the center and single bonds to everything else. Step 3, we're going to add in all our extra electrons. So I'll do that in a different color. So we've already done 2, 2, 4, 6 electrons, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's all our extra electrons. So step 4, 5 are all checks, so we're pretty good there. So here's our shape. So my E domain, I see 3 domains. Therefore, that's trigonal planar. Turns out that's also the name of its Vesper shape. And because it's trigonal planar, we know our hybridization must be sp2 hybridized. And that's it. We can do all the same for number 2. That's going to be, let's try ammonia, NH3. So step 1 for ammonia, you can always pause it, start it on your own. But step 1 is going to be 5 valence electrons from nitrogen plus 1 from each hydrogen times 3. That's going to be a total of 8 valence electrons. Step 2, nitrogen must be in the middle. It's furthest left, lowest quantity, with 3 hydrogens. Step 3, I've drawn 6 already. Now hydrogen is each good with 2, so I'm going to put the final 2 on nitrogen. Step 4, 5 are all checks to make sure we're good. We are. So now I'm going to go into my E domains. So I have 4 domains. That's tetrahedral. For Vesper, even though I have 4 domains, I only have 3 bonds, which I know is going to be, therefore, trigonal pyramidal. Now, for our hybrids, we only care about the domain, and we have 4 domains. Therefore, this is going to be sp3 hybridization. So that is our answer. This is how we figure this out. So that's pretty much all there really is to figuring out hybridization. There's just a few other aspects that we have to understand it in. So the first is, what if we have hybridization across multiple atoms? So in some cases, we have multiple atoms that we have to look at. Well, the key here is that each atom has its own E domain, geometry. Therefore, it would have its own hybridization. So if we look at an example, such as like propene, which looks like this, carbon, double bond carbon, single bond carbon, 1 hydrogen, 2 hydrogens, and 3 hydrogens. We actually have 3 different domains. and we have three different hybridizations. Now, for carbon 1, we have three domains, 1, 2, 3, and therefore this is going to be sp2. For carbon 2, once again, we actually have 1, 2, 3, so it's going to be sp2 as well. But for carbon 3, we have 1, 2, 3, 4 bonds. So for carbon 3, we're going to have sp3 hybridization. And that's how you do it. You just understand that there's going to be different hybridizations across different atoms. And that's all right, because each atom is going to do its own thing with its orbitals to get the bonds it needs to do. So the last and final part of this entire lesson is, what about hybridization in resonance hybrid structures? So when we talk about resonance hybrid structures, you know we're going to talk about benzene, which is kind of like the most famous for it. So I'm going to once again continue to use the exact same image for benzene I always use because I really like it. The key here is that hybridization is based on the bonds. And so what we can do is we can notice that all carbons in benzene have 3 sigma bonds, which means those are going to have to come from hybrid orbitals. Therefore, each carbon has sp2 hybridization. You'll always note that the number of sigma bonds is always equal to the number of orbitals in the hybridization. So 3 sigma is equal to 1 plus 2. So if we have 4 sigma bonds, it would be sp3. If we have 2 sigma bonds, it would be sp. So we can just often look to bonds. The number of sigma bonds is equal to the number of hybrid orbitals. And so you can use that to reference anything. You can even use it to reference ozone. So that central oxygen is going to have 2 sigma bonds, so it'll be sp. So, well, now see, I look at that and I go, wait a minute, this rule doesn't work, because we also have to consider that it's not just the number of hybrid orbitals, but it's the number of hybrid orbitals plus number of non-bonding pairs. You know, you learn something new every day, and looking at that example, I immediately realized that it does not carry with ozone, because ozone does have its lone pair of electrons. So when we're doing this, well, what I should actually do is draw our skeletal formula. So let's just erase all this and look at ozone as its resonance structure. So when we look at ozone in this light, and again, we're only ever looking at the central one, no matter what, we have 1, 2 sigma bonds plus up here, and 1, 2 sigma bonds plus up here. So we're going to have sp2 hybridization within ozone. All right, so now that we've modified this equation, the number of sigma bond, ooh, wow. I wish sometimes this were live so people could correct me. Number of sigma bonds plus number of non-bonding pairs is equal to the number of hybrid orbitals. There we go. Apologies for all of that, but we'll keep it moving with that forward. And you can see my mistakes live because there's no way I'm editing this out. So anyways, I hope this helps you understand hybridization just a little bit more, and have a great day.